Today we're going to look at some temperature conversion calculations from Chapter 7. So in this first problem, we are converting normal temperature of the human body, 98.6 degrees Fahrenheit, to degrees Celsius. So you're going to look at your temperature conversion equations and pick the one that applies most. So if I'm trying to get to degrees Celsius, I want to pick the equation where degrees Celsius is equal to something. And that equation is where we have degrees Fahrenheit minus 32 on the top in the numerator, and that is divided by 1.8. So once you pick the appropriate equation, all you need to do now is just plug in your values. So we're going to take this 98.6 degrees Fahrenheit and plug that in where F is in the equation and solve. So I'm going to have 98.6 minus 32, and these parentheses are important. So if you don't have that top portion in parentheses, it's going to do the division before it does the subtraction, and it's going to give you a different answer. So just make sure you're calculating that subtraction, that top portion first. So when I calculate this out, I get 37 degrees Celsius. So if you were in a European country or even Canada, and you took your temperature, you would hope that the thermometer read 37 since they use Celsius. So let's look at the second question. Liquid nitrogen is 77 Kelvin. We're going to convert to degrees Fahrenheit. So this one is a little more complex than it looks, because if you look at your equations, you'll notice that you don't have one that goes directly from Kelvin to Fahrenheit. So it's going to be a two-step problem. We're going to go from starting at Kelvin, because that's the number they gave us, then to degrees Celsius. Once we're in degrees Celsius, we can then go into degrees Fahrenheit. So let's write the equations we would need for these two steps. So the first step, going from Kelvin to Celsius. So to figure out Kelvin, it's just an addition. You take degrees Celsius and you add 273 to that value. Once we have degrees Celsius, we can then get into Fahrenheit. Now I can't remember if I gave you both versions of this. If I did, you'd want to choose the one where Celsius is equal to. So in rearranging this equation, we're going to put the 273 on the other side of the equal sign. We'll get Celsius by itself, and then Kelvin minus 273. Once you have degrees Celsius, by taking the Kelvin amount and subtracting 273 from it, you can then figure out Fahrenheit. Okay, so now if we want degrees Fahrenheit, we want to pick the equation where Fahrenheit is equal to. And in this case, it's 1.8 times degrees Celsius, multiplication sign here, and then add 32 to that. So let's plug it and solve. So I'm going to start with this rearranged equation for degrees Celsius and Kelvin. So to figure out the degrees Celsius, I'm going to take my Kelvin amount, which the equation said was 77, and I'm going to subtract 273 from that. Notice we're going to get a negative number, and that's fine. That's what the degree sign is for. It means we can go in the negative. So negative 196, and this is, oops, not Kelvin, sorry, degrees Celsius. So that's a very small number. So you'll notice that that's cold, right? It's in the negatives. It's going to be very, very cold. And if you know what liquid nitrogen is, this makes sense. Liquid nitrogen, well, it's exactly what it says. It's nitrogen molecules that have been supercooled so that nitrogen is no longer a gas, but now a liquid. And it can freeze things in seconds. So we have negative 196 degrees Celsius. We're right here. So one more step using this equation is going to get us to Fahrenheit. So I'm going to take my degrees Fahrenheit equation, 1.8, and I'm going to multiply that 1.8 by the degrees Celsius, which I just solved for here. So I'm inserting this, don't forget the negative sign, negative 196 in there, and then I'm going to add 32. What I get is 320. If I want sig figs, I only want 2, so negative 320 degrees Fahrenheit. So obviously very, very cold, right? If you were to get liquid nitrogen on your skin, you would severely damage your skin because it is that cold. All right, let's look at this last problem here. So this last problem, we're given Fahrenheit, much like in the first problem, but this time we're not going to stop at Celsius, we're going to go to Kelvin as well. So just trying to show all of these equations at work here. So if I want degrees Celsius and I have Fahrenheit, I want to choose the equation where degrees Celsius is equal to, because that's what I'm looking for, that's what I'm trying to solve for. So I'm going to use the same equation that I used up there. So I have degrees Fahrenheit minus 32. Remember, that's in parentheses. You need to solve for that first before you divide by the 1.8. So I'm going to go ahead and just plug this in. I have 112 for my Fahrenheit, so I'm going to take that number and plug it into my equation. So 112 minus 32, all of that divided by 1.8. Okay, now 112, that's hot, right? Hot day. So let's see what that would look like if it was in degrees Celsius. I'm getting 44.4. Handwriting's not the best today. All right, 44.4 degrees Celsius. Once I'm in degrees Celsius, I can then go to Kelvin. Notice it's kind of the reverse direction of this problem. We started at Fahrenheit, but then went this way. Okay, so we want the equation K is equal to degrees Celsius, because that's what we have. I'm going to plug that in right here, plus 273. All right, so let's get my 44.4. I'm going to add 273 to it. I get 317. Kelvin. All right, so that's temperature conversion. You've seen pretty much every type you'd ever be asked on it. So next we're going to look at heat calculations. So now we're going to look at those heat calculations. So I have two problems on the board here. One is calculating the heat needed to raise the temperature of 100 grams of copper from 22 degrees Celsius to 40. So whenever you see the word heat, okay, that's that letter Q. So the equation that we'll be using is MC delta T. And remember, all delta T means is change in temperature. So another way to write this equation would be MC, and then instead of delta T, you would write TF for final temperature minus TI for initial temperature. All right, so let's go ahead and write down all of our variables. So we need a mass. So looking through this equation, it gives us a mass, it's in grams of copper, so that's 100. Okay, we also need a C value. So if you remember, C means specific heat, and that's dependent upon the type of material. So in this case, we're talking about copper. So we would need to look it up on a table if it wasn't given to us, find copper on the specific heat table, and figure out what that value is. So if you look up on the table, it's 0.094 calories per gram times degrees Celsius. So remember, those units help you remember what you need all of the other variables in. So just double checking that value. Notice for mass, they gave it to us in grams, and we're so used to converting that to kilograms right away, but not for this equation. We want to leave it in grams. Okay, so we have M, we have C. Now we're looking at the delta T part, the change in. So notice they give us two different temperatures, so we need to figure out which one is the final, the TF, and which one is the initial. So it's going from 22 up to 40. So the final is going to be that 40 degrees. Our initial then being the 22. So now let's plug all of this into that equation and solve for heat. Now, since I'm raising the temperature, since the temperature is being increased, I suspect my Q value will be positive because heat is going into the system. It's usually a positive heat, a positive Q value. So I have 100 for the mass, then I'm multiplying by the specific heat, which is 0.094. And then I'm going to take my final minus my initial, so the 40 minus the 22. Plugging all of that into my calculator. 0.094 times 100. I get 169. And remember, the units for heat, even though it's a form of energy, we're not using joules like we did for work and kinetic energy and potential energy. We're using calories. And if you ever are not sure on that, just look at the units present on the specific heat value, because it tells you you need the calories for the Q. You need grams for the mass. You need degrees Celsius for the temperatures. Okay, so 169 calories of heat is required to raise the temperature of that copper from 22 up to 40. All right, so let's look at the next equation. Now this one, problem, this one is asking for heat again. Okay, so we're looking for that Q value. So we know we're going to be using this equation or one of these variations. This time we're raising the temperature of 1.6 kilograms of a cast iron skillet. Okay, so the kilograms is the mass, but remember, we don't want it in kilograms. We want it in grams. So my first step is going to be to convert 1.6 kilograms to grams. So it's a metric to metric conversion, so I can use that King Henry died drinking chocolate milk. What's going to go in that empty space is a G for grams because we're looking at mass. So we're at kilograms, we're at the K. We want to be at the G, so we move the decimal point 3 times to the right to get it there. Okay, so starting with my number, my 1.6, I'm going to start at the decimal point and I'm going to move that decimal point 1, 2, 3 to the right, just like I did up here. What's going to go in those empty spaces are zeros. So 1.6 kilograms is equal to 1,600 grams. So this value is what I want to use as my mass. So I'm going to erase this section and I'm going to label that 1,600 grams as with the variable m for mass. So m is 1,600. Okay, so next I need to look for my C value. We just said by reading this problem that it's a cast iron skillet. So I'm going to go to my, if I still have it open, table of specific heats, and it says iron specific heat is 0.11. So 0.11. So I just looked that up on a table. Calories, grams, times degrees Celsius. All right, well notice in this problem, they only gave us one temperature. 35 degrees Celsius. So they didn't give us a final and an initial. What did they give us then? Let's see. How much heat is needed to raise the temperature by 35 degrees? So this 35 degrees, while it's not a final or an initial temperature, what it is that whole delta T. They're saying, I want the total change in temperature to be 35 degrees. So this, I would use this top equation, since I only have one temperature, and in place of this delta T, that's where I'm going to plug in my 35. So now I can go ahead and solve now that I have all the variables needed to solve for heat. So I'm going to take 1600, multiply that by the specific heat of iron, in this case 0.11, and then by my delta T, which is 35. So let's plug that into my calculator here. I've got 1600 times 0.11 times 35. I get 6,160. Units, since it's heat, we measure it in calories. So it will take 6,000 calories of heat to increase the temperature of that cast iron skillet by 35 degrees. So the last problem we're going to look at is this aluminum material that we are cooling from 55 down to 27. So aluminum specific heat is 0.215, as I know I'm going to need that at some point. So we're still calculating heat, just like the other problems. So we're using either the equation with a delta T or the equation with final temperature minus initial temperature. And just glancing at this, I'm given two temperatures, so it's going to be that last one there. Let's make the list anyway. It just helps to organize things a little bit better. So mass, 35 grams. Is grams okay? It is for the heat problems, yes. Next, I need a C value. So for that, I'm looking at the type of material. In reading this, it says aluminum. So looking up the specific heat of aluminum, I think it was 0.270. Nope, 0.215. So let me fill that in. And then there's two temperatures, so we need to figure out which one is the final and which one is the initial. Well, in this case, they're saying heat was lost. So I'm going to guess that the smaller number is going to be the final. Because if heat's lost, that means that the final temperature is lower than the initial. Okay, it's also saying it cools from 55 down to 27. So the second number is usually the final. So I'm going to put 27 degrees Celsius as my final. Then I'm going to put 55 degrees Celsius as my initial. Let's plug these values into the equation. So I have 35 for my mass. I'm going to multiply that by the specific heat of aluminum, 0.215. And then I'm going to take my final temperature of 27 and subtract my initial 55. So notice 27 minus 55, that's going to give you a negative number. So we're going to have a negative specific heat when we solve for this. And that makes sense because the object is cooling down. It is losing heat. So when heat is lost from a system, we get a negative Q value. Remember, units are calories. So negative 211 calories because heat was lost. And the other two problems we did, heat was being gained. Heat was going into the system, so we had positive Q values.